Okay, welcome everybody. Sorry for the couple-minute delay. We did have a couple of technical difficulties. We are excited to welcome you to our virtual session. My name is Lisa Lamb. I'm the President and CEO of the Lewis Center for Educational Research. And together with Goldstone and NASA JPL, we are excited to bring our next installment of the NASA in Your Neighborhood talk series. Today, we're going to learn about Parker Solar Probe, which is humanity's first mission to a star. And to introduce our very distinguished guest speaker today is Dr. Joe Lazio. Dr. Lazio is the Chief Scientist of the Interplanetary Network Directorate at JPL. So Dr. Lazio.
Thank you. Thank you, Lisa. It's my pleasure to introduce Dr. Phyllis Whittlesey. She is the Associate Director of the Heliophysics Group at the Space Science Laboratory at the University of California, Berkeley, and also the instrument scientist for the SPAN instrument on the Parker Solar Probe, about which she's about to tell us. Dr. Whittlesey studied at the University of Alabama in Huntsville before coming to the Space Science Laboratory at Berkeley, and her research focuses on how the sun produces extremely high-speed ejections of matter and how those can be measured using spacecraft instruments. Her work involves extensive use of the data transferred from spacecraft through the Deep Space Network. Phyllis?
Great, thanks so much, Joe. So yeah, that was a fantastic, introduction. Can you guys see my screen okay? Can someone just tell me if you can see the appropriate thing?
Yes,
I see it.
Okay, great. Yeah, it looks like I suffered a technical thing for a moment there. Great. So I'm going to keep this pretty simple for the most part and talk a little bit about exploration and use NASA's Parker Solar Probe as an example of an exciting mission that does make, in fact, extensive use of the DSN in the early days of solar probe right after launch. I think there wasn't a day where I was not glued to the DSN activity because it just absolutely blows my mind that we have this space Wi-Fi internet and people are just like, DSN, what are you talking about? So yeah, I'm really excited to give a talk to this audience in particular. Let's see, how do I go through my slides without looking silly? I don't know that this is in fact working. Hold on 1 second here. Seem to be suffering an issue with presenting. There we go. Okay, so all right, I can send a spacecraft to the sun, but I can't figure out how to share my slides. So this is who I am. My name is Phyllis, and I've been a space nerd most of my life. The picture on the left was taken when I was probably like 10. And I think it's in front of one of the Gemini capsules. The Gemini capsules are the Gemini mission, rather, that project was the manned mission right before the Apollo series of missions that took us to the moon. They sent up 2 astronauts at a time to do spacewalks and practice maneuvering around in space and gathering the skills that would be required for us to have a successful lunar landing on the moon with human beings. And the picture on the right was taken about 2 years ago in the clean room at Florida prior to the Parker Solar Probe launch. And that's me in the clean room suit standing in front of the spacecraft. And I'm happy to say that that spacecraft has so far broken the fastest vehicle record 5 times running now. Because that's the number of times that we have been close to the sun. So yeah, our top speed's like 480,000 kilometers per second. I'll talk about it later in the presentation, but I am a real human being and this is where I came from and this is what I like. And I study.
Just 1 second,
Yeah.
Phyllis, I have somebody who has typed in the question, one of our participants, that they cannot hear anything. I'm wondering if any of our other participants, I am monitoring the question. So if anybody can type in if you are able to hear and just see if that's an individual problem or if it's, okay, I can hear, able to hear. So, okay, thank you guys. So most are able to hear you. I'm not sure what's going on. For this one individual, but I'll be monitoring questions, so keep them coming.
Okay, great.
Sorry.
Yeah. And I suppose, I don't know what format you guys prefer, but I'm happy to take questions as I go along too. So I'll just keep going until I'm otherwise interrupted. Great, so I study the sun. This is the view of the sun that we see from every day. Heats our entire planet, keeps us hot, keeps us warm, powers all of our plants and animals and creatures as we go along the surface of the sun. But the sun is actually a star, and it's one very specific type of star. This is a picture from Hubble. This is like one of these great deep field images. And when trying to explain why it is that I spent 7 years of my life building a spacecraft to go to the sun, I think it's important to remember that the sun is just a star. And when you look up at night and you see all of these stars from far away that are, hundreds or thousands of light years away, we can't yet go and visit those stars and look at them and see why, for example, in this picture, they're different colors. We can't, go and touch and smell and see them. We can't visit them, but we do have a star in our local neighborhood, and that local star in our local neighborhood is the sun. So when you think about why would we bother to go and get as close to the sun as humanly possible, right? It's really hard to do because, as it turns out, the sun is kind of hot. And part of that motivation is, well, this is the one sun that we have in our own personal space laboratory. So anything that we don't know about our universe and all the foreign and beautiful and exotic stars that might be out there, we can use our sun as an example of trying to figure out why, for example, stars are different colors. And I have a little quick explanation here on some of them. Just bear with me a second. There we go, I'll click forward. So this is one of my only astrophysics slides before I start jumping into the sun and solar exploration. This is a really beautiful graphic that some people at NASA made talking about the different types of stars. So in that previous picture, that deep field from Hubble, some stars are brighter than others and some stars are different colors. And essentially, the only thing that differentiates stars from each other is how old they are. That's this, actually, I think I can pull a little pointer out here. You guys will probably be able to see this. So how old they are, which is this direction here. If you start over here, you have baby stars and they get older as you go in this direction. And then their size, or how heavy they are, really how much mass, how much matter they're made of. And that is this y-axis here. So essentially what this shows you is that for stars that are small or not very massive, they start out as a protostar, a baby star, right before it actually begins to become its own self-igniting ball of stellar gas, right? It can become this little brown dwarf, and it stays a brown dwarf its whole life. And as you work your way up on this picture, which I love this picture, if a star is a little bit more massive, then as soon as it becomes an actual star and makes its own light and begins undergoing nuclear fusion, you can have a red dwarf star, which might get a little bit bigger as it gets older. And then eventually it'll end as just a small white dwarf star, a little tiny pinprick of really hot, super dense matter. And then as you go up, you get something like our own sun. So you have this, again, baby star with a little more matter than these two down here. And a sun-like star starts out, roughly yellow colored, as opposed to a red dwarf, which, as you might guess, is red. So a sun-like star, yellow star, eventually will get to become a red giant. So it changes from this yellow to this red color. And then eventually, as it gets older and older, that star gets bigger and bigger until the star can no longer hold on to those outer layers of atmosphere, and they just drift away in these beautiful planetary nebula, and you get this white dwarf star. Moving all the way up, sometimes you get a really massive star that forms a giant blue, or in this case, a blue supergiant star. And these are very unstable stars. And they just basically go straight to an explosion sometimes. They just explode because the nuclear processes and the energy generation inside of them is so sporadic and chaotic that they just explode. And then that material later goes on to make other stars, which could be anywhere along in here. So the one that I study is just this one here in the middle, a sun-like star, a yellow star. And in fact, when we look out at the universe and we look for habitable planets that might be able to support life, usually they're these type of stars with this particular mass, a really narrow range of stars, if you would. So how do we know all of these things about stars? How do we know anything? If we can't go and visit them, and we can't touch them, and we can't taste them and smell them with any of our other senses, the only thing that we can do is look at them. And we look at them from this one place, our planet Earth. I like to show this picture because this picture was taken by the Apollo 8 astronauts. The Apollo 8 astronauts were the first humans to ever leave close Earth orbit. They didn't land on the moon, but what they did is they went all the way out to the moon and they circled around the back side and they came back. And as they came back up over the limb of the moon, which is this gray part you see, they saw the Earth. So for the longest time in humanity, the only thing that we knew, all of what we knew about, space, stars, planets, it was all taken from just looking from this little outpost, either with telescopes or with eyes or with whatever we had. And as humanity becomes more advanced, we can start to send people or robots in our stead to go investigate, like these people that took this picture. They took it from the other side of the moon. And we can actually start to interact with space, which is new. We've really only been able to do this for the last 60 years or so. So it's a very exciting time for anyone that's interested in space or the heavens or stars, because now we can send people or we can send robots in our stead to go explore those outer regions of space. So these are 3 different spacecraft from 3 different times. This one over here is a famous space robot explorer, if you will, called Voyager. And it got launched from the Earth and went all the way out to the outer, it's actually left our solar system at this point. There were 2 of them. And so it went by Venus, no, not Venus, it went by Jupiter, Saturn, Uranus, and Neptune, all the way out through the solar system. It was launched in the 1970s. In the middle, obviously, we have Hubble. So the Hubble Space Telescope, which is that where that image of all of those stars a couple slides ago came from. The Hubble is actually in low Earth orbit. So technically, it's still kind of pictures taken from the Earth or very close to the Earth. From all of these really far away places. And then this picture over here is actually a spacecraft called Juno. And Juno is orbiting Jupiter right now. And it has a couple imagers you guys might have seen through different news articles, these beautiful pictures of Jupiter. And this spacecraft can actually go and be present and touch and smell and see. I'm saying smell like human senses, which will come be more apparent later, but can actually go to those places and interact with these planets. And that's incredibly new for us on the time scale of things. And all of these things are really only possible because, again, of the Deep Space Network. Anything that travels pretty much beyond the moon, you have to have really big radio antennas in order to be able to contact. So all of these pictures come through stations like Goldstone. Yeah, so in studying the sun, this is actually a painting from the 1500s. And this is a painting of a solar eclipse. And I bring it up because you have this, really great image of the sun, and it's got this dark thing in the center here. But you'll notice all of this yellow around the edge. And that yellow around the edge is actually what Parker Solar Probe was designed to study and designed to go and touch and not just look at from afar. But again, like I said before, for the longest time, the only thing we could do was observe with our eyes from really far away and examine the light alone. So during a solar eclipse, you actually get a chance to see the sun's atmosphere, that corona, that you don't really get a chance to look at the rest of the time because the sun's surface is so completely bright. You can't take a look at the atmosphere, which is still quite bright, but not nearly as bright as the solar surface itself. We have modern pictures. In fact, this is a picture of a solar eclipse from only a few years ago by these people down here who graciously took this picture and made it available on the internet. And you can see this dark disk actually isn't the sun, it's the image of the moon that we see because it's blocking out the surface of the sun. And these wispy pieces, these like streamers, as we call them actually in our field, that's the solar atmosphere. And it's not an atmosphere the same way that we think of here on Earth. It's actually confined by magnetic fields because the sun is an extremely magnetic object. It has this huge magnetic bubble that extends all the way out past Pluto. And we live inside of that magnetic field all of the time, this big bubble barreling through space. And when you look at the corona, you can actually see, if you've ever seen like a picture of a bar magnet's magnetic field, you can see this rough magnetic field shape, like these lines sprouting out the top and the bottom of the Earth. And in fact, some of those magnetic field lines begin to form loops, but they get pulled out really far. And they get pulled out really far by this wind that is constantly coming off of the sun that we also live within. So when you look at the surface of the sun, itself, this is not the corona, this is just the surface of the sun. You might think that it's featureless, but in fact, it's not. In fact, sometimes we see these little spots on the surface of the sun. Sometimes there are a bunch of them during what we call solar maximum, when the sun is really active and there's very complex magnetic fields. And sometimes you see not very many of them. In fact, there's actually a sunspot on the surface of the sun right now for anyone that's interested in looking at it. This is not that sunspot. But when we see these on the surface of the sun, then we know that there's magnetism, there's magnetic activity. And they're actually cool regions that are cooled by some sort of magnetic activity on the surface of the sun that we may or may not understand. This is another image of the sun, and I'm trying to bring all these pictures up to just really show you that we can learn so much just by looking at the light coming from the sun. This is another image taken not in visible, but probably in ultraviolet light. And you can see these really chaotic, you know, wispy, twirly, those are all highly technical terms, by the way, magnetic field structures on the surface of the sun. This one would probably correspond with one of those sunspots I was talking about earlier, and some of these as well. So some of these lines, you can see they just go out into space and they might go on out forever. Some of these form giant loops, which, by the way, are really large compared to the Earth, like much larger than the Earth. And this is all to show that the sun isn't just a big empty ball in the sky, it's actually really dynamic. So if we see this on our personal star of this one specific subtype, you know, we can try to guess what stars in our sky might look like up close, particularly by looking at them through different wavelengths and sections of light. This is a video, first video of the series. This is actually a video from a spacecraft called SOHO, and it is images of just the sun's corona. So before I click play here, I'm going to point out a couple things that aren't real. One, this black line that you see isn't real because it's holding up this big dark disk in the center. And this dark disk in the center isn't the sun, it's actually just blocking out the sun and some of the sun's atmosphere. And the little white circle that you see in the center is actually representative of the sun itself. So this is showing you how really dynamic this atmosphere, this corona of the sun can be over time. And every now and then you see these explosions coming off, these little burps, if you will. They are big explosions of gas, so I suppose that's appropriate. And those are these really big explosions on the surface of the sun that release tons of energy. Sometimes they hurtle towards us here on Earth and create things that we see, aurora, for example. And I'm showing this video to say that we know what they look like, and we know that they contain a lot of energy. By the way, this is false color. The sun is not really blue. I'll continue to play it. But we don't really exactly know why they happen. We know sometimes that these big explosions on the sun, these ejections, we call them coronal mass ejections, sometimes they're correlated with sunspots and regions of magnetic activity, and we know that they're highly magnetic. But sometimes they're not connected at all. Sometimes they're connected with big bursts of X-rays that we see from the sun, things that we call solar flares, and sometimes they're not. But this is, you know, a nice, really up close and personal look at how dynamic and energetic a star can be, and really affect us here on the Earth in ways that I'll get to later. So this picture is a little bit of a brag. This is just a picture of all of the different parts of our solar system, and it's to point out that this mission that we have, Solar Probe, is actually really exciting for a lot of different reasons. One is that for way back in the 1950s, scientists were asked by our government to try to come up with ways of using access to space, like rockets, to do science in space. And so we have traveled to all of these different planets so far, right? We've gone to Mercury and Venus and Earth and Mars and Jupiter and Saturn and even Pluto, even though technically it's not technically a planet anymore. And up until 2 years ago, we hadn't yet gone to the sun, which is really the driver of this entire system. So we're with the launch of Solar Probe 2 years ago, we actually have been able to slowly, very slowly over time, spiral in close to the sun and try to understand what maybe those impulsive events, those ejections on the sun, where they come from and how they form. Because I have to say, we haven't really been able to figure that out just by looking from afar. So this is another image just showing you how big these ejections can be. This is actually a solar prominence. It's just a large loop of plasma and gas that can sometimes form on the sun associated with really strongly magnetic regions. And this is the Earth in comparison, like it's extremely small. So yeah, it's just interesting to think that these huge prominences could affect us here on Earth so much, and we don't really have a very good idea of how to predict them all of the time. So yeah, again, here's a really nice another picture. Here's the size of the Earth next to some of these features on the surface of the sun. So to go and actually look close, and not just look close, but try to fly through the sun's atmosphere. And instead of just looking at the light that we have from it, trying, and you can think of like a spacecraft like a human stand-in, and the way that humans interact with our environment is we look at them and we, if you don't know something for the first time, you might pick it up and see how heavy it is or touch it, or try to hear if it makes any sounds. Or I don't know, for the adventurous of us, we might try to taste things. And none of those things are possible when we observe from the Earth. So in order to understand more about our sun, we built the spacecraft, the solar spacecraft, to actually go there and try and engage in other ways to measure what's actually going on at the sun. So this is the spacecraft here in the center. It's small. I showed a picture of me with it at the very beginning of this presentation. It's only like 2.5 meters tall. Most of it, in fact, at the front is made out of heat shields because, like I said earlier, as it turns out, going to the sun, it's hot close to the sun. So as you look at this, we have these nice like antennas because we're going to measure electric fields that we might measure close to the sun. There's a nice white light telescope over here. We have different particle detectors. You can think of particle detectors kind of as like the nose of a spacecraft. What they do is they're looking for electrons and ions, so negative and positive particles that you might measure in the sun's atmosphere because it's highly charged, it's fully ionized plasma as we travel through it. And much in the same way that a nose counts particles, you can if there are more particles, you might smell a smell more strongly. That's essentially the same thing that we're doing with these. In terms of like an instrument that you might have on Earth, it's basically like measuring the wind. So we're measuring the wind that's close to the sun. We launched on August 12th in 2018. We launched on a Delta IV Heavy, should be a Delta IV Heavy with a custom upper stage. So going to the sun, it turns out, is actually really hard. So instead of going straight there, we have this nice long winding path. So I have in this picture over here, this plot of the Earth's orbit, of Venus's orbit, of Mercury's orbit, and finally the sun. And this is not an image of the sun to scale. But we launched, and then we very slowly over the course of almost 7 years, wind in very slowly. And we do that by using 7 Venus gravity assists. So we're not just getting chances to encounter with the sun, we're also getting chances to encounter with Venus as well. So as we pass Venus, we drop in a little bit closer, which is where you see the next ellipse. At the end of our encounter will actually be less than 10 solar radii. That's solar, half solar widths from the surface of the sun. And the front of the spacecraft, and this is why it's all made out of heat shield, it'll actually be over 1,000 degrees hot. So the front of the spacecraft will actually glow red whenever we get really close. Currently, we are on this ring right here, the third one in, and getting closer all the time. So yeah, solar powered spacecraft because we're going to the sun. We also have magnetometers and so on and so forth. And like I said before, we hold the fastest vehicle record for any man-made object. That is 450,000 miles per hour. Altogether, we'll be doing this for about 7 years. So just to give you guys an idea of how these explosions on the sun could affect us here on Earth. So here's this nice cartoon image of the sun, and you can see it's got this magnetic field that we have illustrated, and there's these nice magnetic field lines contained in these prominences, and sometimes those can turn into these coronal mass ejections, which you can see is this big, nice front, this explosion on the sun that moves supersonically, in fact, towards our Earth. And while we're living here on the Earth, we also have our own magnetic field. It's what makes compasses work. But this magnetic field is highly compressed because of this extremely fast wind, not just these ejections, but this extremely fast wind that is constantly blowing over the Earth. And anytime there is a change in that wind speed, it compresses our magnetic field and just squeezes it on the top and the bottom and then the front a little bit. But what happens when you get one of these giant coronal mass ejections is that it actually injects a lot of energy into our sun. It can also induce currents in electrical grids all over the planet. So trying to understand and predict when these coronal mass ejections happen, when they might hit Earth, when they might not hit Earth, is a really important point for us as we live in this environment with this really dynamic star. So this is just explaining a little bit about how some of these things might affect us here on the Earth. For example, these currents that we could induce in power systems, like I said before, also they might induce currents in pipelines. You know, you might, if you're flying over in a flight over the top of the Earth, you might get more radiation than you might get otherwise. Some coronal mass ejections have actually been known to kill spacecraft, just inducing electric discharges when we might not expect them. In fact, sometimes those spacecraft are actually inside of Earth's magnetic field, and then you get compressed even more and sort of expose these spacecraft to space outside of Earth's magnetic field, and then they get shorted out and we can't drive them anymore, and then we're very sad. But it also affects things like GPS. So if you've ever been somewhere and your GPS starts to act haywire, you can just blame it on a coronal mass ejection. It might not actually be it, but you'll sound relatively smart and interesting. So that's my personal plug for that. Right. So other than that, I do want to say that there are at least two weird things, and this is a little embarrassing, that we don't really understand about the sun. We understand somewhat, but not fully. And the first one is, I have a picture of campfire, and you might be wondering why. And I ask you to think about, what would you think if, as you moved away from a campfire, you felt hotter? And that is actually something that we see on the sun, and that is that the surface of the sun is about 5,000 degrees. But when you get up into the atmosphere, it becomes millions of degrees. Now, that doesn't make a lot of sense. You think the sun should be the hottest thing in our solar system, and you would be right. At its core, it is the hottest thing. But the surface of the sun is much colder than its atmosphere, and that just doesn't make sense. Physicists don't really like this. Things are, it's supposed to get colder as you move away from the hot thing. And so, barring weird laws of physics that we don't understand, there has to be some energy that's actually heating the atmosphere of the sun. And we've talked so much about magnetism so far, and that makes magnetism a really great candidate for a mechanism to actually actively heat the sun's atmosphere, the corona, to millions of degrees. And there are a couple different theories, and hopefully these videos will work as intended. One of them is when you look at the surface of the sun, and this is a bit of an older video, but when you look at the surface of the sun, you see all of this motion, this shaking, if you will. These little grains, we call these little circles on the sun, we call them granules. And as they move around, if you can imagine a little magnetic field line connected to it, and then it spins around and circles and tumbles and twirls, then you might get something like this little cartoon image up here, where these swirling patterns on the surface of the sun could cause shaking of those magnetic fields. And if you think about plucking a guitar string and it releases that sound, sound doesn't travel in space, but there's another type of wave that travels in space that's essentially electromagnetic and not acoustic, like you would expect from sound. And if there's a way to dissipate that wave into the atmosphere, well, that's a heating mechanism. So maybe these turbulent motions on the surface of the sun can create heating and heat the atmosphere to millions of degrees. Because again, like it can't, like the laws of physics say that as you get away from a hot thing, you're supposed to experience less heat. So that could be a potential mechanism for heating the solar corona. Another potential mechanism for heating the solar corona, again, I have a image here. Hold on while I click the play button. Here we go. This is from a rocket called High C. And this is not in the visible light. This is actually an ultraviolet. But what we see here is an up-close video of a particular spot on the sun. In fact, it's associated with a sunspot. And you see these nice little bright loops appear. And those bright loops appear and change as you see this rapid change in all of these lines over here. So I'll play it again in just a moment, but when you start out, you'll see this little loop of light plasma over here, and then all of a sudden something changes and these little bursts change their shape. And when something like that happens, you can get a large release of energy. See, there it is right there. It sort of changes all of a sudden. You see all of these, looks like a wind blowing down there at the bottom, to be honest. So you see this loop and then it changes all of a sudden and you get these loops that appear over here. So that's a particular process called magnetic reconnection. And essentially what it means is if you have a loop here of magnetic field and you have this other thing here, they can touch and release a ton of energy. And that might also be another process that could potentially heat the solar atmosphere, as these reconfigurations of these loops and whirls on the surface of the sun, if they have enough of those impulsive events, then they might actually be responsible. Let's just watch it one more time. They might actually be responsible for releasing all of that energy that could heat the solar atmosphere. I just think this video is so nice, so I like to watch it. I think there should have been text on this slide, but yes, here we go. So what do we have on our spacecraft to try and measure what type of heating is happening? So like I said, some of those waves are electromagnetic, and so that means that you can measure them by their electric fields, or you can measure them by their magnetic fields. So we have these nice electric field antennas and we have magnetometers, but you also want to know how hot it is where you are. So we have different sensors on the spacecraft, on Solar Probe, that can measure the temperature of what we see around us. We also have a camera. So we can see, there's this nice little camera down here called Whisper, and it takes pictures not of the sun directly, but it takes pictures of the sun's atmosphere as we're going through it sideways. We also have an anemometer. These are the types of instruments that I build that count particles. They measure wind speed. They can also figure out what the temperature is. And we also have the ability to make measurements of our magnetic field. So we have a couple magnetometers that can measure magnetic fields. And altogether, through the 5 orbits that we've had so far, we've been able to make pretty successful measurements so far of heating. I would say that so far we probably haven't, well, we haven't really gone in as close yet as we think we need to be able to actually measure those heating processes, to actually watch that plasma be heated in place as we go through. But so far we actually have made a couple interesting measurements. These are the 3 basic science questions. We want to trace the flow of energy. We want to determine the structure and dynamics And we also want to explore mechanisms that accelerate and transport energetic particles. And these are associated with those coronal mass ejections, like I said before, those explosions on the sun. So far, what we've discovered through Solar Probe is actually that this wind that we see coming off of the sun isn't nearly so steady as we thought it was. In fact, you saw those videos earlier of the surface of the sun twirling down here, and it seems like we actually see some of those whirls as they propagate backward. So we see these large kinks and regions where this supersonic wind coming off of the sun actually turns around and flows back towards the sun. Very briefly. And so this is a big mystery for us right now. Scientists are actually actively debating about what these are, whether they're important, whether they're interesting, whether this is even what they look like. So this is an interesting active field of research. We call them little switchbacks because as you look along these streams, they sort of go forward and then switch back on themselves again. And it's been quite interesting for us to take a look at. And that is actually the end of my presentation. I like to leave a lot of space for questions. So I don't know how you guys would like to do questions, but I guess at this point, I'll hand it over back to the organizers again to open the floor for questions from people.
So we have, go ahead and type your questions into the question box. And then I have them. Marcy, did you want to read off the questions or did you want me to do that?
Sorry, Lisa, I think we're having some technical difficulties. They're too small to read on our end.
It's Marcy. If you don't mind reading them, that would be great. Thank you.
Okay. All right. Here we go. Phyllis, the first one is coming from Sarah Dujak. And her question is, how did you test the probe and or the materials to see if it would be able to withstand the sun's temperature at perihelion?
Yeah, that's a great question. Actually, it was really hard to do. As it turned, I mean, it is because, on Earth, there's a okay, I could talk about this all day long. I'm going to try to not, though, because I'm sure there are other questions. In fact, I'm just going to go back a couple slides and show a couple pictures, if that's okay. Yeah, let's find a good picture of, yeah, this one will work. Okay, so, right, this whole thing was pretty small and it's going to the sun, which is really hot. And you'd think that making things really hot on Earth wouldn't be that hard, which is true, except that it's not just that the spacecraft is getting really hot, it's also getting really hot in the vacuum of space. So materials behave very differently in a vacuum than they do in atmosphere, right? The atmosphere that we have, that we live in all the time. So there's a facility in France that takes the entire side of a building and it tunes all of the mirrors and it focuses all of these mirrors onto a single spot. And that spot contains a big metal tank that you can pump down to a vacuum, which is just a big vacuum chamber. And so we took samples of these materials. The front of this shield, by the way, is made up of stuff that's really similar to the gray part of the space shuttle. It's like a type of reinforced carbon and carbon foam, another special secret sauce, I'm sure. And so we just tried to test small parts of all of the metals first. That turned out to be really hard because, not just because we don't want them to melt, but because a lot of these instruments, like these electric field antenna, for example, we want this material to be electrically conductive, and not just conductive, like electric conductivity can change over a wide variety of temperatures. Something that's really cold might be really conductive, but if you heat it up a lot, it might not be conductive anymore. It might be insulative or vice versa. So the best thing that we did was we actually took the entire spacecraft and we put the entire spacecraft in a vacuum chamber and put a bunch of heaters in front and tried to heat it up, but not too much. Because there's always this fear that you destroy this beautiful spacecraft before it ever gets a chance to fly. So there was a whole part that was just this. This is all radiator and this is all heat shield. They took built a model of just this and actually heated that up to the point where it might be destroyed and tested to see if it worked, and it worked. And that process gets repeated over the entire spacecraft. A lot of equipment was destroyed in that process, but eventually it happened. The name of the game is all just trying to make your test environment as space-like as humanly possible, which isn't always easy. So I hope that was a good answer to your question. Yeah, a lot of sleepless nights over that.
All right, here's the next one from Siddharth Chandra. And the question is, how do sunspots relate to CMEs?
Yeah, we don't know. We think that coronal mass ejections, let me see if I can't pull up that video again and have it rolling while I'm talking about this. I tried to get my video working earlier and it wasn't quite working. So usually I would just gesture with my hands a lot, but instead I'll have to deal with these videos instead. Right, so these big coronal mass ejections usually come from close to where those sunspots are. And those sunspots are, we see lots of really tightly, actually I'm gonna go to a different slide, I changed my mind. They're really close to, here we go. So this is a nice picture of the sun, and you can see the red lines here are magnetic field lines, and these little black spots are actually supposed to be sunspots. And you see in this picture, at least, we have these lines that go from sunspot to sunspot. So if you see a sunspot, often it'll have either a little companion gray dot with it, or it'll have another companion sunspot somewhere nearby. Not always, but a lot of the time. And that is because you see these magnetic field line has to come out and it has to go somewhere. So it goes back into another sunspot again. So we think that when the magnetic field here gets twisted enough, something explosive happens. Maybe something like, I'm gonna skip forward to that other video again, something like this, right, where you have these lines of plasma can sort of be thought of as proxies for those magnetic fields. And something all of a sudden changes and the configuration changes. And because of that configuration changing, that bunch of hot superheated gas that's showing up here is really bright white. It gets released on the surface of the sun and it gets to fly off freely. So you know, the sun's environment's really different from anything we interact with here on Earth. You can interact with magnetism and you can interact with heat, but rarely do you interact with magnetized heat, if that makes any sense. So whenever you see a video like this on the sun and you see these lines, you can think of them as really hot plasma frozen to magnetic field. And again, going back to those videos of the coronal mass ejections. So whenever you see, where is it? There we go, this one again. So whenever you see these little puffs coming off, right, and they look like light bulbs sometimes, or little, bulbs coming off, those are really tightly wound magnetic fields that get released off of the surface of the sun, and then they're just allowed to flow away, or at really high speeds. So there, I hope that was a good answer to that question.
Okay, perfect. All right. The next one is from Curtis Franklin. What part of the Parker mission are you most looking forward to getting results from?
Oh, well, that's a great question. That last encounter is going to be really cool. At some point, I didn't even get to talk about the solar wind. The solar wind coming off of the sun is actually supersonic, right? So extremely fast. And what does that mean in space when, like, you don't really have enough air to travel quickly, or, you know, for sound to travel through at least? And that just basically means that the wind coming off of the sun travels faster than any wave can travel through it. And at some point, that wind coming off of the sun has to be accelerated to be supersonic, right? Because it's not just born here and, you know, supersonic all of a sudden. At some point, it has to travel to something that's supersonic. So that'll be cool, being able to find that point where you see the solar wind rather become supersonic. That'll be really exciting. And what else am I really excited about? Oh, I know. So the sun's activity, rather like the number of coronal mass ejections per year and the number of sunspots that we see, that actually like cycles up and down on an 11-year period. some people say it's a 22-year period, but for our purposes, we'll say it's an 11-year period, where you'll see for, you know, a couple years, which was the way that it has been for the last few years, you'll see no sunspots. You won't see many explosions on the sun. You know, the sun mostly looks like a big yellow featureless thing, like here, except without the sunspot. And then you have solar maximum, when you have spots all over the sun, lots of coronal mass ejections, flares of X-rays coming off of the sun. And right now, so Solar Probe has had, we're actually on orbit 6. We just finished our 6th encounter of the sun a couple weeks ago. We are a quarter of the way through the mission, but the last 2 years have been during solar minimum. So there hasn't really been a lot of really impulsive, explosive things happening so far. But I fully expect that over the next couple years, as the solar activity ramps up, we'll get to see more explosions on the sun up close, and that'll be really cool. Like if we get a chance to have one of those coronal mass ejections passing over our spacecraft, that'll be extremely exciting and also terrifying because, well, there's a lot of energy in those, and I hope we don't fry. Thanks, Curtis. That was a great question.
Okay, the next question is, how do ground-based observatories around the world provide help in collecting data?
Yeah, that's great. So ground-based observatories are extremely helpful because our little spacecraft, our little Vanguard spacecraft, there wasn't a lot of space to put all of the instruments on it that we might want. And in addition to that, because it's really hard to make a telescope or a camera point directly at the sun, like look directly at the sun at close proximity, basically the thing that you're never supposed to do. Ground-based observations are really important for understanding what we're seeing as we're passing through. So I'm going to go back to another image. As we're passing through the atmosphere, for example, and we have one of these explosions on the sun pass over us, we'll really want to know where that came from. And, you know, we can't actually point the cameras on our spacecraft at the sun's surface itself as we're passing by. So we have to wait for periods where Solar Probe is in a position where it can see the sun, but also the Earth can see the same part of the sun as well. There's a particular type of measurement made by some observatories on the Earth called a magnetogram, and they actually image magnetic fields on the sun. So the images themselves are, I think they're beautiful, but they're black and white and gray. And magnetograms, I think, are really useful for us to try and understand where the wind that we see blowing over our spacecraft comes from the surface of the sun. That'll be really helpful. In fact, that's something that a lot of people on the team are trying to figure out is when will we have these conjunctions of the Earth and Solar Probe and the sun in the same region, and how can we best optimize those observations together?
Okay, the next one comes from Linda Singley, and she wants to know, can you see the difference in temperatures or speeds of particles of different charges or types?
Can we see different
differences
speeds in particles
temperatures?
of different charges or types? Yes, yeah, actually. And this is an interesting consequence of being in space, is that ions and electrons behave very differently in space, and they behave differently at different energies. An ion, like a proton, most of what we see in the solar plasma is all protons with some helium atom core, we call them alpha particles, some of those coming through, but pretty rarely, mostly just protons. Those particles almost always just stream out from the sun, right? So flowing away outward. Sometimes they do little loops, and that's about it. Electrons, on the other hand, you can think of the electrons in space, at least in the solar wind where we live, as like a giant soup. They're sort of sloshing back and forth over everything all the time. I mean, they are escaping from the sun at some point, but electrons will bounce off of anything. So an electron could come off the sun and it'll go see Mercury and bounce off Mercury and come back and then see a magnetic field and bounce outward again. And so electrons are bouncing all over the entire solar system all the time. And we see that actually at Earth with spacecraft that are orbiting the Earth. We see electrons coming from all directions. There's a specific subpopulation of electrons though, and they are called the strahl. And you can think of them as like the laser beams of the solar plasma, I guess. And those strahl really follow those magnetic field lines very closely. So those are like nice tracers for magnetic topology. The speed of those particles, as we get closer to the sun, we expect them to change. But even at Earth, we can see that those particles have different speeds. So I hope that was a good answer to your question. If not, feel free to follow up because I have a lot of, it's a matter of how deep down the rabbit hole you'd like to go.
Okay, all right. The next question comes from Robert Baker. He would like to know, what is the max temperature at perihelion?
Oh, yeah, great question. We would love to know too. We have a lot of estimates, and in fact, here's an ironic thing about going to the sun with this little spacecraft, right? So the front of the spacecraft, I haven't shown you the front of the spacecraft because all the cool stuff's on the back. The front is basically a big white disk. But all of these other instruments, there's a few instruments that actually stick out into the sun. There's this one here, it's called SPC, it stands for the Solar Probe Cup. And then there are these 4 electric antennas. They're part of a Fields suite. They have been tested up to probably over 2000 degrees. And I have to say, I can't remember if that's Celsius or Fahrenheit, but either way, it's really hot. Ironically, though, all of the instruments that sit in the shadow, like the ones that I build that are down here, are actually some of the coldest sensors of their types that we've ever flown before. So just from the front of the heat shields, which goes from at least over 1000 degrees at closest approach, down to about here, you'd lose like 1000 degrees. So up here, you could be 1000 degrees Celsius, and down here, we're at like minus 60 Celsius. Really cold because there's no heat input. All you see is just the blackness of space. We have seen the temperatures go up as we get closer. And then I have something disappointing to say, which is that the engineers who built the spacecraft, and rightly so, were so concerned about imperfections and anything that could cause this heat shield to crack, because if this thing cracks, like, we are totally hosed. I'm trying to find a nice PC word to use that. We're completely hosed. They did not want to put a thermocouple on either the front or the back. I don't know how you would on the front or on the back of the spacecraft. So as we get really close to the sun, we won't know the precise temperature of the front of the spacecraft, but it will almost certainly be over 1500 degrees. I'm going to say Celsius.
Okay.
Great
All
question,
right.
Robert.
The next question is from Patricia, and Patricia would like to know, can your research help us develop ways to shield our electronics from the next active solar period?
Yeah, that's a great question. Shielding from energetic particles that are associated with coronal mass ejections and solar flares, it's really hard to be clever with that, because energetic particles can travel through metal. Well, they can travel through a lot pretty easily. Some materials are better at stopping that penetrating radiation than others, but most of them are heavy. I think that what we hope to do as far as improving our predictions of space weather, because a lot of this research falls under the big umbrella of space weather. People often say that space weather prediction is where ground and Earth weather prediction was, like, I don't know, insert a number 40 years ago. Not that great. We're getting better at it though. And in fact, this mission, I think, will help us predict better when we can expect to see things like coronal mass ejections based on things that we observe over the next 5 years. But I think what with those models that we develop, I think that we'll be able to have better resiliency for like the entire power grid, for example, or be able to better divert flights or put spacecraft into safe regions of orbit that would prevent them from getting damaged from those energetic particles associated with coronal mass ejections. There is some space weather that's being done, not by this, well, yeah, by this project in part, but as far as like materials themselves go, I think that it's really hard to do that. Now, when you design electronics for a mission like this, you have to think about how things like cosmic rays, for example, which are really energetic particles that come from outside our solar system, or solar energetic particles that come from our sun and can be associated with one of those coronal mass ejections. You have to think about how to make your electronics resilient to it. And it's not really in materials, but there's specific techniques that people can come up with to check for things called bit flips, right? So if you have memory in your computer, it's just a way of recording ones and zeros. And if you get a cosmic ray that comes through at the right moment and it hits a 1, it can turn it into a 0 or vice versa. So what they do when they build spacecraft sometimes is they'll make 3 copies of the same thing that's recorded in memory and put them on 3 different chips. And then if you have to access that, they'll like look at all 3 copies. And if 2 copies say that bit 32 is supposed to be a 1 and 1 copy says that bit 32 is supposed to be a 0, you can probably assume that the other copy got corrupted. And that's something that's done on a lot of spacecraft like this. So good question, Patricia.
Okay, Siddharth has another question for us.
Yeah.
Does the temperature of space have an effect on the overall heat of the sun?
Does the temperature of space have an effect on the overall heat of the sun? Wow, what a deep question. That's interesting. I think I'm not entirely sure what that question is getting at, but what it made me think of is, does the cold blackness of space suck energy out of the sun? And I think it probably would, but I think that there are many other larger effects that are occurring within the sun itself that would override anything that you would measure from that cold space vacuum effect. For example, the sun currently uses nuclear fusion of hydrogen to make helium as the source of its energy. And it's slowly running out of hydrogen. And as that happens, and as it's losing mass, because all of this wind that's coming off of the sun has to come from somewhere, the sun's force of gravity, I'm playing fast and loose with physics terms, but as the sun's force of gravity will actually lessen. And as it becomes less massive and the gravity force becomes less, the layers of atmosphere of the sun will actually loosen. And you can think of it as like the sun puffing a little bit. So over time, the sun will slowly start to puff up a little. And I think that those effects and effects like that would probably have a larger effect on the temperature of the sun than the vacuum of space. But it's an interesting and somewhat deep question that I'm going to think about later. Really good questions.
These are really great questions. Okay, we're going to keep them coming. Angel would like to know, going back to understanding how it's hotter than the surface of the sun, do you believe gravity might be another factor to consider?
Is gravity another factor to consider? Yeah, so there is a theory that says, so yes, but it's a little more complicated than you might think. Let me see if I have a picture to go along with this. I don't think I do, just kind of a shame. This one will work. Yeah, actually this one might work after all. So if you think about how gravity works on different particles, and on gases. Like if you look at the sun, if you look at the atmosphere of the Earth, for example, and you take a cut of it with regards to height, you'll see that there are different percentages, like the mix of gas in the Earth's atmosphere is actually different as you go up. And that all has to do with how energetic those gases are at a specific temperature and how energetic they can be without escaping the Earth's gravity. It's a similar thing on the sun, except it has to do with the way that gravity interacts with protons and electrons. So a proton is 1,000 times heavier than an electron. And very differently from Earth's atmosphere, protons and electrons both have charge. So it's thought that electrons can reside, and this is very, very close to the sun, in fact, so I'm going to pull up a different picture. Yeah, let's pull up a picture like this. So very, very close to the sun, like close to the surface of the sun, and then outward, right? So very close to the sun, you have ions and electrons, or rather protons and electrons. And those electrons might be hovering a little bit higher than the ions. This is all a theory, and it's not necessarily a theory that I subscribe to, but it is a theory, so I'll give it the time of day. There's a thought that because the electrons can hover a little bit higher, and because they have charge, and because the ions might be a little bit lower, and because they have charge, that sets up an electric field. And the thought then might be that that electric field sort of sets up this like railgun effect. Railgun isn't exactly right, but you set up this electric field that accelerates particles out. And there's a theory that that actually might explain the acceleration of the solar wind. And I think that's, if you want to read more about it, that's a theory called exospheric theory, EXO, spheric theory. And it is actually a stellar astrophysics theory. So it could be possible that that's part of the effect. And ultimately, when we have to look at how to explain the heating of the corona, it's incorrect to say that any one mechanism is responsible. What's likely, and what we're seeing really, is that there are several mechanisms that are contributing to the heating of the solar corona. At this point, we're just trying to figure out which ones dominate and when.
Okay.
Again, like really good questions.
Yeah, these are really good questions. Mark Wanis would like to know, why are there multiple magnetic fields on the sun, unlike the Earth?
Yeah, that's great. How should I explain that best? Why are there multiple magnetic fields on the sun? I think the best way to explain this is to look at what's happening deep inside of the sun and to compare the difference between the two. This is probably a good picture because it has the sun and the Earth. The Earth gets its magnetism from its molten core. I'm not a dynamo expert, but the dynamo experts tell us that there's a hot molten core of iron at the core of the Earth, and the motion of that core is what gives the Earth its magnetism. And that magnetism is pretty basic because of the simple rotation of the Earth. And because of the motion of the core is likely also relatively simple compared to the sun. The sun, on the other hand, is not a solid object. It's more like a big liquidy, hot ball held together with its own gravity. But you know, if you had a suit that could survive any temperature, you could dive into the sun, much the same way that you could dive into Jupiter if you wanted. There's not a solid surface on that planet either. But because the sun is so hot, most of the gas, all of the gas, I'm just going to say all the gas, even though it's probably like 0.001% that isn't held under this big broad statement I'm about to say. Most of all the gas is highly magnetized. And by that, it's like the motion of those particles, the motion of charged particles can create magnetic fields. So the way that their magnetism forms is a little bit different, right? One, you have hot liquid core of iron moving. And iron, I think, is pretty familiar for a lot of people that think about magnets. And then the other one is this hot plasma that's moving. So because the sun is liquidy, and because you have this plasma, the appropriate conditions can be set up, and in fact are set up, where the sun's atmosphere and the liquidy layers that we see on this surface can actually drag those magnetic field lines around. And if I go to another one of those videos that show that magnetism, right, like this one, like all of that little motion, all of that's dragging and stirring magnetically with the sun. And this comes with a big fat caveat that we actually haven't ever cut into the sun. So a lot of this is theory, and it's based off of what we see and what we know about magnetism. But the 11-year solar cycle of the sun is also a bit of a mystery. Like, we've observed the solar cycle back since the 1600s, or even before then, people have been recording sunspots. So we know that this cycle, this 11-year cycle of, the sun's magnetic field becoming more complicated and less complicated and more complicated over the cycle of 11 years. We know that that's been going on for a really long time. But if you ask my personal opinion, I think, and this is, I'm almost a layperson when it comes to that type of solar study. If you ask my personal opinion, I think that perhaps as a species, we have not had the tools to observe those cycles for a long enough period of time to determine why that 11-year cycle exists, for example. And that 11-year cycle is very closely related to the complex origins of the magnetic field. So a bit of a, I hope that's doesn't read too much as a cop-out, but it really has to do with the fact that the sun is made of molten plasma, which is charged and moving a lot, versus a hot metal core in our Earth that's moving in one direction, more or less. Great question, Mark.
Okay, we have
Mark,
a few
right?
more questions. Are we still good to take a couple more?
Oh, you're asking me? Yeah, I'm fine.
Okay, all right. So Sarah would like to know, do we know why there are solar minimum and maximum periods?
Yeah, not really. It's actually a current field of research. We think that it has to do with the winding of magnetic field within the sun. Let me see if I have a picture that I can draw on. I think drawing might be an option. A big picture of the sun somewhere. Yeah, this one might work. Give me one sec while I try this thing out. Okay, so if you have the sun, it's got roughly a big old magnetic field. Okay, this is a terrible drawing on a trackpad. But right, you have like these big curved features that you see in the sun's magnetic field. The magnetic field also travels within the sun itself. So perhaps yellow isn't the best color for this. I'll pick red for the inside of the sun. Here we go. So big old magnetic field lines inside the sun. But the sun is rotating. And the funny thing about the sun being liquid is that the center of the sun, rather the middle part, pick a different color here, the middle part of the sun actually rotates a lot faster than the top and the bottom. So because these field lines are sort of stuck to the sun, the ones that are drawn in red, I'm just going to draw those again. What you get over time is this like winding up of magnetic fields. I'm going to draw a big ol' cartoon drawing of what that winding looks like. So instead of having just, lines straight up and down, those field lines get wound as the center of the sun, or rather the part closer to the equator, winds and spins faster than the top and the bottom. It's this like differential rotation is the word for it. So we think that the 11-year cycle of solar maximum and minimum is related to how much winding the sun can take before little bits pop out and look for relief. It's like if you take a piece of plastic. When I was a kid, I played with pen caps a lot. So I would like sit there and like twist and twist and twist the like stem part on the pen cap until finally it broke. That's essentially the same thing that's happening. There's like some tension, some amount of magnetic tension that the sun can take until eventually those things pop out. And that's really the sun rapidly reconfiguring itself to be in a less complicated magnetic field state. But it is still an active area of research. Again, like fantastic questions.
Yeah. Okay. Robert has a question. Are there more elementary particles like mesons detected close to the sun?
Mesons. I think
Mesons,
that's
sorry.
mesons.
Yeah,
Yeah.
mesons.
I have to say, I actually don't know the answer to that question. I'm not a particle physicist, but I do know that we expect to see more free neutrons close to the sun, but we don't have a neutron detector on Solar Probe. There's another European mission that isn't going as close to the sun as Parker Solar Probe. That mission is called Solar Orbiter. Very creative with these names. And that spacecraft might have sensors that would be able to detect those types of particles, but I'm afraid I don't know the answer. But if you shoot me an email, I'll do a little research and see if I can't give you a better answer. Here, I'll put my email up in the front. That way, if people want to know or send me an email and ask a question, you can feel free to do so.
I want to say these are some great questions coming from Gabbard students all around the country. So it's pretty exciting. Okay.
I'm excited.
Yeah. So the next question is another question from Siddharth, and he would like to know, when you're nearing the sun, doesn't it push you back? How do you counter that?
Yeah, it does actually, a little bit. The answer, and that's really great. So what's pushing us back, it's a combination of the solar wind, right, which is pretty diffuse. It's not very dense, but it is a wind and it does exist and it does exert a small amount of force. There's also photon pressure. So photon pressure is just the pressure from light. And it's a small amount of photon pressure. It's a lot bigger force when you're close to the sun compared to far away, but it does exist. What that force that's generated by the solar wind hitting the spacecraft and by the photon pressure, those forces are extremely small compared to how fast we're whirling around the sun. So here, I'll go back to this plot of our orbit. I think that might be the best slide to talk about with this. So when we go in here close to the sun, like, we're going so extremely fast. Like, oh, how do I say it? Probably more than 10 times Earth escape velocity. We're just so extremely fast. And so the momentum that we have going sideways dwarfs that pressure that we have coming from the sun to push us away from the sun. It does happen a little bit, but not too much, because again, our momentum is so large. What does happen, however, is if this heat shield is off, like if it's not perfectly centered, then what happens is the spacecraft can turn. And so what happens constantly when we are in a solar encounter, a close solar encounter, is we have gyroscopes that are constantly spinning to counteract any of that turning from the spacecraft not being completely and perfectly balanced. Of course, whenever the spacecraft is made, we try to balance it as best we can, but there's no way you're ever going to get it 100% perfect. So the spacecraft does turn a little bit from those forces of pressure, but it doesn't push us significantly away as much as you might think, because again, our angular momentum is so large.
Okay. Robert would like to know, can a wobble start in flight of the probe, and how long would the probe last?
A wobble. Can a wobble start and how long would it last? So I'm not sure what Robert exactly meant, but I will say spacecraft can be uncomfortably floppy things. So while I have this picture up here, you see this nice little, extension behind the spacecraft. This is our magnetometer boom that holds we have a little 3-axis coil magnetometer here and a couple others on here. And it's way back here to get away from the spacecraft and any stray magnetic fields that might be on the spacecraft. This thing tends to be floppy. So anytime you have a thruster fire on a spacecraft, it's going to apply a force about the center of mass, and this thing can tend to wag, which is a little uncomfortable. Spacecraft are great in zero gravity, and when still. But sometimes little thrusters like that can form oscillations in either antenna or in booms like that. And in general, the instruments that are on those portions of the spacecraft can actually see those effects. They tend to damp pretty quickly. When we first deployed this piece, actually, I'll go back to another picture. When we first deployed that boom, it launched in a stowed configuration. It's actually in this piece of plastic here, like wrapped up alongside the spacecraft. When it first deployed, there was a lot of motion and it took a few days for that to calm down, but eventually it did. So I hope that's a useful question. If not, please follow up. I'm happy to try to explore the answer with you.
We're going to take our last couple questions here. The next one comes from Siddharth. This probe seems to have machine leaning. Correct me if I'm wrong, but how do you train the probe to analyze different situations from Earth?
Oh yeah, that's great. One of the most complicated parts of this spacecraft was the flight software, actually. I wouldn't necessarily say it is intelligent necessarily. Like, I don't think that it would employ some of like the machine learning techniques that you might think of. Everything is very, how would you say? Here we go, this one again. Very deterministic. So the way that the software is tested is you have a list of conditions that could occur and you test the software in every single one of them. It is true, however, that when we're close to the sun, so in this region, again, there's no communications with the spacecraft at all, except occasionally we have beacon tracks. So if something goes wrong, we won't really know what went wrong until after the spacecraft travels back out again. And it's, say like here on out. And that's all controlled by flight software. I cannot state enough, like the flight software on this project was extremely complicated and it has to control a lot. It has to control like how far out the solar panels are folded, how much water am I pumping through the radiators, where am I pointing? And then there's all of the normal like guidance and control and gyroscopes driving that has to be done. There are also, I don't know if you can see on your screen wherever you are, there are these little things on the bottom and on the sides that look like mini blinds. Those are louvers that also help control the temperature of the spacecraft, and all of that is done automatically. It's truly incredible how autonomous the spacecraft can be, because for up to 15 or 20 days when we're close to the sun, no one's behind the wheel. It's just going completely on its own. And when you have a new encounter where you go closer to the sun, the entire team will get an email every couple days saying, oh, we got beacon tone A. Beacon tone A means nothing has gone wrong and all the systems are working as they are. And everyone's always relieved. Some people can't take it. They just go on vacation for those 15 days because they can't stand the wait. It's a great, very perceptive question though.
Okay, the last one that we're going to field is from Sarah, and Sarah would like to know, can any of the information we gather from the probe or sun enable us to find habitable zone exoplanet stars easier?
Oh, that's an interesting question. I'm not sure. That's probably not an answer that I should give. Let's see, can any of the data that we get help us better find habitable planets around other stars? I would say probably, but not specifically. Like as we understand, here we go. As we understand the life cycle of our own star better, we will understand better about how the age of other stars that we see will affect habitable zones. So habitable zones around stars currently are defined by a range of temperatures you would expect a planet to be with a specific type of atmosphere, or maybe not with a specific type of atmosphere, away from that parent star. And as we learn more about this star, the sun, and how it changes over time, I think that definitely would inform us better about how other stars are. That's an interesting question. Yeah, maybe not specifically, but in the grand scope of filling in the gaps that we have about understanding other stars. I think that it is probably an interesting and important piece of that puzzle. Yeah. Again, really great question. I'm going to think about that one tonight for sure, you know, like as I'm going to sleep probably.
So one thing I want to share, some of these students are working almost independently with Nancy, one of our Gaver operators. So it seems like maybe doing some of this work and some of this exploration just on their own time. So I just have to say, I was really impressed by the level of questions, especially from some students who are in middle school.
Yeah, no kidding.
Yeah, so that's exciting. So at this time, I want to, if there are no more questions, I wanted to turn it over to Heather Doyle from JPL.
Great. Hopefully I can share my screen too. Thank you for that wonderful discussion. Let's see, am I sharing my screen now? I don't know if I did.
I don't see yours yet. Yes, now I do. Well, I know I don't. Sorry. What an amazing presentation, though. Phyllis, I have to say, we've hosted many of these talks, and you have to be one of the best speakers that we've ever had. Thank you so much.
Thank you very much. I really appreciate it. Actually, I have to say, I sweat giving talks for the public more than I do for my fellow scientists because, you know, I think it matters more. Thank you.
Yes. Yes.
I don't know what I did. So you don't see my screen?
I don't right now. Ryan, are you able to help? Ryan's joined us back again. So thank you for everybody hanging on. Hang on just one more moment. We don't want you to go yet.
Basically, let's see. That's all right. I just wanted to make sure that folks know that this afternoon, the mission called OSIRIS-REx is going to be touching down or tagging up with an asteroid called Bennu, and it's going to collect a sample at that time. And that sample, if they collect enough, will then be returned to Earth. So it's the first of its kind. So that's this afternoon. So if you go to NASA on social media, some news stations are also following it, as well as you can also go to DSN Now, which is an application that shows you live what the DSN antennas are looking at. So you can see OSIRIS-REx. Yeah, thank you. Yes. You can see OSIRIS-REx communicating there at the bottom. They're talking to Canberra, so they're talking to Australia and also Goldstone, where you are. Some of you are, I shouldn't say all of you. And then also, if you go to, well, I better not do that because I can't give the exact. EYES also has a solar system application on the solar system website where they're showing what Bennu looks like. So check that out. Just wanted to put that on your radar too if you like all things NASA. That's a pretty big thing that's happening today as well.
Today is a big NASA day. Okay, are there any other comments from any of our panelists, or Phyllis, did you want to say anything to wrap us up?
Oh, I just wanted to say, like, I'm a huge fan of that DSN webpage. I think I always have that open on a tab on my laptop somewhere, and I'm just looking to see like where we're communicating with, you know, these like foreign space probes all over the solar system. I find it so cool. And also, I'm really excited about OSIRIS-REx. So other than that, thanks everyone for coming and for listening, and feel free to shoot me questions. I love interacting and answering people's questions, especially insightful ones like you guys gave today.
All right, thank you so much. This was a wonderful talk. For all of our Gabbard students online, keep running sessions with us. We'll continue to bring you NASA in the Neighborhood talks several times a year and present awesome opportunities. So thank you to everybody for participating today and learning a little bit more. Today is a great day for NASA.
We should also note, Lisa, you should also note it's a great day for the Lewis Center.
Oh, yeah, yesterday was our 30th birthday, so we're very excited sharing our anniversary. And so our partnership with NASA has been almost as long as our entire livelihood or being, and just it's exciting to see where we've been in 30 years and where we're going to go next. So thank you, Dr. Lazio. All right, thank you all. And we'll post this, we'll record it and post it so that you can watch it again.
Thank you.
Thank you.
Thanks.